Good day, students. Welcome to part one of the mixed review series on limits. So let's go ahead and take a look at question number one. So question number one, we need to find the limit as x approaches 4 of 2 times the square root of x plus the square root of x. Okay? All right, so to evaluate this limit, we can just plug in the value that x is approaching, so we can evaluate this by substitution. So this is going to become 2 times the square root of 4 plus the square root of 4. Okay, let's go ahead and reduce this. This becomes 2 times the square root of 4 plus the square root of 4 is 2. So your final answer is going to be 2 root 6. Okay, so there you have it. All right, number two, let's find the limit as x approaches negative 2 of 4 over x plus 2 times x divided by x plus 2 times x. Okay? All right, let's go ahead and figure out what the value of this limit is. So first thing we can do, we can cancel out, but how about, we have an x down here. So if we distributed this x to this quantity in the numerator, it will get rid of this x in this denominator right here. So rather than dividing downwards, which would be a natural inclination, we'll just distribute this x to these two quantities in the parentheses. So that yields the limit as x approaches negative 2 of 4, because 4 over x times x is 4, plus 2x divided by x plus 2 times x. All right? Now we can factor out a 2 in the numerator and write it in standard form. So limited as x approaches negative 2, factor the 2 of 2 times x plus 2 divided by x plus 2 times x. Okay? So what happens is that these x plus 2's divide out. So what we're going to have is the limit as x approaches negative 2 of 2 over x. Now I've simplified it as much as we can. So what we're going to do now is basically substitute. So this becomes 2 over negative 2. Your final answer is negative 1. All right, so there you have it. Okay, let's take a look at question 3. So, for question 3, we want to find the limit as x approaches negative 2 from the right of x times the square root of x squared plus 7x plus 10. Okay, so all we do here is we can just plug in negative 2 from the right in here and see if we run into any issues with the domain. If not, we can just evaluate it. Okay, so let's go ahead and evaluate it. We're going to have, by substitution, negative 2 from the right times the square root of negative 2 from the right squared plus 7 times negative 2 from the right plus 10. Okay, all right, let's go ahead and simplify this. This piece out here, we can write this as, just write it as negative 2 times the square root of negative 2 squared is 4. 4, and then multiply this minus 14 plus 10. All right, if you simplify this entire expression, you have negative 2 times 4 minus 14 plus 10 is 0. And your final answer is negative 2 times 0, which is 0. All right, so there you have it. All right, let's move on to question number 4. So for question 4, I want to find the limit as x approaches infinity of 3x sine 2x. Okay? All right, so if we make a direct substitution, what we're going to have is 3 times infinity sine 2 times infinity, right? 3 times infinity we know is infinity, but what is sine of 2 times infinity, which is the same thing as sine of infinity? At infinity, sine goes between -1 and 1. It attains any value. It oscillates between -1 and 1. It doesn't approach any particular value. So this is going to be oscillating between negative infinity and infinity. So since we have an oscillation there, so since the limit oscillates, since the limit oscillates, it doesn't have a particular number that it approaches, okay? Oscillates, the limit does not exist, okay? The limit does not exist. All right, let's take a look at the next problem, problem 5. Now let's find the limit as x approaches negative infinity of x squared times x plus 5 times 2x minus 3, and this whole expression divided by uh, the square root of x to the fourth times x to the fourth plus 2. Okay? All right, so now since we're going to negative infinity, we can look at uh, the weights here. Okay, what's the weight of the numerator and the weight of the denominator? If you expand it completely, what we're looking at is we're going to be looking at x squared multiplied by x multiplied by 2x. And in the denominator, we're going to be looking at the square root of x to the fourth multiplied by x to the fourth. So the leading term of the numerator after expanding it completely is going to be 2x to the fourth. And that's all we care about is the leading coefficient, the leading term. In the denominator, the leading term is going to be the square root of x to the 8th. All right, so we're going to take that limit as x approaches negative infinity. And then let's simplify it a little bit. We're going to have the limit as x approaches negative infinity of 2x to the 4 over, and if you simplify the denominator, the square root of x to the 8 is the same as x to the 8 over 2, which is just x to the 4th. Okay? So these x to the 4ths divide out, and then that leaves you with the limit as x approaches negative infinity of 2, and then your final answer is simply going to be 2. All right? So there you have it. All right, let's take a look at question number 6. So on question 6, we have, let's find the limit as x approaches 2 of x squared minus 4 divided by x to the third minus 8. Okay, so if we plug into directly into this this expression right here, we're going to have 2 squared minus 4 over 2 to the third minus 8. We're going to have 0 over 0, which is undefined. So let's inspect this, go back to this expression, see if we can reduce it, factor and reduce it, and then substitute 2 in. Maybe that undefined value is as a result of a removable discontinuity and not an infinite discontinuity. Okay, so let's factor out the numerator. X squared minus 4 is the difference of squares, so we can use the formula a squared minus b squared equals a plus b times a minus b to factor that. And then for the denominator is the difference of cubes. Um, so we can use the formula um, a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. Okay? All right, so that's what we're going to use to factor the denominator. All right, so let's go ahead and apply these two formulas here. It's going to give us the limit as x approaches 2. The numerator factors into x minus 2 times x plus 2. That whole thing divided by, and if you factor out the denominator, you're going to have x minus 2 times x squared plus 2x plus 4. Because in this case, a is x and b is 2. Okay, just simply take the cube root of these two terms to figure out what a and b are. Okay, so there goes the factored form, and we can see that the factor causing the non-existence of the limit is a removable discontinuity. So even though we have a removable discontinuity at positive 2, that doesn't mean that the limit is non-existent there. So let's go ahead and divide or remove the discontinuity from the expression. We're going to be left with the limit as x approaches 2 of x plus 2 divided by x squared plus 2x plus 4. Okay, so now we can just go ahead and plug in 2 into the expression. We'll have 2 plus 2 divided by 2 squared plus 2 times 2 plus 4. So we're going to have 2 plus 2 is 4. 4 over, this is 4 plus 4 plus 4. 4 times 3 is 12. Divide top and bottom by 4, you're going to end up with 1/3. Okay, so there goes your results. All right, let's take a look at question number 7. What if we want to find the limit as x approaches 2 from the right of 6 minus 3x divided by the absolute value of x minus 2. Okay, so we can rewrite this as the limit as x approaches 2 from the right. Reverse this order. We can write it as negative 3x plus 6 divided by plus or minus x minus 2. Okay? Now we can rewrite this as the limit as x approaches 2 from the right. In the numerator, we can factor out negative 3. So we're left with x minus 2. And the denominator, since we're approaching 2 from the right, we're going to take the positive piece of this plus or minus sign. So it becomes positive x minus 2. Okay? Had it been we're coming from the left, this would be negative. Okay? So since we're coming from the right, this is positive. We take the positive piece. So these two quantities divide out. So we now have the limit as x approaches 2 from the right of negative 3. But negative 3 is independent of the direction that this limit approaches, so your final answer is negative 3. All right? So there you have it. All right, let's take a look at problem number 8. So for problem 8, what if we were to find the limit as x approaches 0 of the square root of 3 minus x minus the square root of 3 divided by x. Okay? So this one, if we plug in 0 directly, we'll have 0 in the denominator, which results in an undefined result. So this is an example where we have to rationalize the numerator. Okay? So to rationalize the numerator, we'll multiply the numerator and the denominator by the conjugate of the numerator. Okay, you get the conjugate of the numerator by switching the sign in the center. Okay, in the numerator and also in the denominator. All right, now let's multiply this out. So this is going to give us the limit as x approaches 0. If you, this is a difference of squares, so consider this being a minus b times a plus b. Okay, a minus b times a plus b equals a squared minus b squared. Okay, so if you multiply that out, this is simply going to become the square root of 3 minus x squared minus the square root of 3 squared. That goes for the numerator. Okay, and then for the denominator, we're going to simply have x times the square root of 3 minus x plus the square root of 3. Okay, let's not distribute because we might have some cancellation happening in the top, that'll take out this x, all right? So this gives us the limit as x approaches 0. In the numerator, the square and the square roots cancel out, so we have 3 minus x minus 3 divided by x times the square root of 3 minus x plus the square root of 3. Okay? You notice that these two 3's add up to 0, and then we have that negative x there, which we can divide the top and the bottom, but let me write it down again. So we have the limit as x approaches 0 of negative x divided by x times the square root of 3 minus x plus root 3. So we can now divide out this x, okay? And then now we can plug in 0 without any problems, okay? So if we plug in 0, this is going to become negative 1 over the square root of 3 minus 0 plus root 3. Okay, so that becomes negative 1 over 2 root 3, because 1 root 3 plus 1 root 3 is simply 2 root 3. Okay, so now let's rationalize the denominator. You multiply top and bottom by root 3, root 3. So your final answer is going to become negative root 3 over 2 times 3 is 6. So there goes your final result. All right, let's take a look at problem number 9. So for problem number 9, for the given function, determine if the limit as x approaches 4 of f of x uh, exists, and that's for the A part, and B, uh, determine determine if the function is continuous at x equals 4. Okay? Alright, so the function under consideration is a piecewise defined function given by x squared minus 5. If x is less than 4, the square root of x plus 9. If x is greater than 4, and pi if x equals 4. Okay, so this is a piecewise defined function under consideration. All right, so we're going to approach the function from the left and the right to see if it approaches the same value. If it does, then the limit exists. So let's give ourselves a number line to have a solid idea of what the picture looks like. So this is the value. 4 to the left is less than. We're dealing with this function x squared minus 5. That's when x is approaching 4 from the left. And then from the right, we're dealing with this function, the square root of x plus 9, is when x is approaching 4 from the right. And then when we're evaluating f of 4, we're simply going to be looking at the constant function, which is pi. Okay? All right, so let's go ahead and consider each case. So for the limit, the a part, the limit exists if the left and right hand limits are the same. Okay, so let's find the left hand limit first. Limit as x approaches 4 from the left. We're going to be using the function that's active on that interval, which is x squared minus 5. So plug in 4 from the left, square minus 5. That's the same thing as 16 minus 5. Directionality is not really relevant here. So 16 minus 5 is 11. Okay? Now, from the right, we're going to compute the limit as x approaches 4 from the right of the square root of x plus 9 equals the square root of 4 from the right plus 9. Okay, square root of 4 is 2 plus 9 equals 11. So the left and the right hand limits are the same. That means the limit exists. Okay, so since the limit as x approaches 4 from the left is equal of the function is equal to the limit as x approaches 4 from the right of the function, and they're both equal to 11. That implies that the limit as x approaches 4 of the function exists, and it's equal to 11. Okay? So this b part is continuity. Is the function continuous at 4? F of 4 is equal to pi. Okay, based on this piecewise defined function we have up here, f of 4 is pi, so that actually is not equal to the limit. Okay, it's not equal to the limit as x approaches 4 from both sides. So since they're different, that means that the function is discontinuous. Is discontinuous at x equals 4. Okay, in this case, we have a jump discontinuity since these are the two, yeah, it's just, I'm sorry, it's not a jump, it's a removable discontinuity or point discontinuity since the limit exists for the function at that point. Okay, so the function is discontinuous there. All right, number 10, let's find the limit as x approaches 0 of sine 3x over 4x. Okay, so remember the formula for this, if you have the limit as x approaches 0 of sine ax over bx, your limit is simply going to be a over b. Okay, using the squeeze theorem. So let me show you why that's the case here. So to show you those steps, I'm going to multiply top and bottom by 3 because I want to make it look like I want to make the argument of the sine function and the denominator identical. Okay, so multiply top and bottom by 3. You want to make it look like the limit as x approaches 0 of sine x over x, something like that. So what I'm going to do is I'm going to toss this 3 to the front of the limit, move this 4 out, and then insert this 3 in the place of the 4. Okay? So what will happen is this is going to become the limit as x approaches 0. The 3 goes in front of sine 3x over, oh yeah, 3 to 4 goes out 2, and then the 3 goes in place of it, 3x over 3x, okay? Using the squeeze theorem, we know clearly that this entire limit is going to go to 1, so this becomes 3 over 4 times 1, and then your final answer is 3/4. Okay, so there you have it. All right, let's try another example. Um, number 11. Let's find the limit as x approaches plus or minus infinity of sine 3x over 4x. Okay, so for this one, remember that the limit as x approaches plus or minus infinity of sine x over x is equal to 0. Okay, so this we expect this to go to 0 by the squeeze theorem. Okay, so to show you why that's the case, I can multiply this by the same 3 and 3 so that the argument of the sine and the denominator will be the same. So we're going to have 3 times the limit as x approaches plus or minus infinity of sine 3x over 3x. Now this 4 we can put over here. Okay, so this entire limit is going to converge to 0 because this oscillates between plus or minus 1, whereas this gets infinitely large. It becomes an infinitely large negative number or an infinitely large positive number. Okay, so this becomes 3 over 4 times 0, and your final answer is 0. Okay, so Good day, students. Welcome to part two of the mixed review series on limits. So let's go over the following review problems on limits. Problem one. Um, let's find the limit as x approaches 4.9 from the right of the floor of 3x over 2. All right. So in this problem, we can see that we don't have any issues with direct substitution of this value that x is approaching into the function. So we can just go ahead and substitute it. So we're going to have the floor, our greatest integer of 3 times 4.9 from the right, that divided by 2. Okay? Then simplifying further, we'll multiply 3 by 4.9. So we're going to have the floor of 14.7 divided by 2. All right? So what's the floor for 14.7? So what the greatest integer function does is it rounds it and a non-integer to the greatest integer that's less than that non-integer. Okay, it rounds integers to itself. So the greatest integer that's less than this non-integer is 14. So it basically rounds it down to 14 over 2. And 14 divided by 2 is 7. All right? Okay, let's take a look at question number 2. Um, for problem 2, we are to find the uh, vertical and horizontal asymptotes and then you're to uh, verify your vertical asymptotes using limits. Okay, asymptotes using limits. And the function under consideration is f of x equals the square root of 8x to the 6th minus 4x to the 4th, and that entire expression divided by x to the 3rd minus 2x. All right, we're going to start off by looking for the horizontal asymptotes. So let's write down horizontal asymptotes. All right, so to find the horizontal asymptotes, we're going to let x go to plus n minus infinity. And any numerical value that it approaches, finite value it approaches, as it goes to plus or minus infinity, that will be a horizontal asymptote. Okay, so let's go ahead and start by heading to infinity. So we're going to find the limit as x approaches infinity of the square root of 8x to the 6th minus 4x to the 4th over x to the 3rd minus 2x. All right, so when you're looking at the limit at infinity, the leading term in the numerator and the denominator are what we're going to focus on, because the other terms don't go fast enough at infinity. So in the numerator, I'm going to focus my attention on 8x, the square root of 8x to the 6th. And in the denominator, the leading term is x to the 3rd, so that's where I'm going to focus my attention on. Okay, so at infinity, the only thing that's the count, limit as x approaches infinity, is going to be the square root of 8x to the 6th divided by x to the 3rd. Okay, and then when I take the square root of the numerator, I'm going to have the limit as x approaches infinity of the square root of 8 times the absolute value of x to the 3rd. Anytime you take an even root, you add the absolute value component there over x to the 3rd. Okay? All right. Now, this is going to become, now when we're going to infinity, we know that this absolute value is going to attain a positive sign, right? So let me just show you the steps. limit as x approaches infinity. 8 can be reduced into 2 root 2 times this can be written as plus or minus x to the third over x to the third. Okay, don't be in a haste to cancel because you don't know what direction it is yet. So I'm going to write this as 2 root 2 times the limit as x approaches infinity. Since you're going to infinity, it's going to take the positive sign, okay? So it's going to be positive x to the third over x to the third. So what happens is entire limit becomes, this divides to 1, so it's going to become 2 root 2. That's your limit as x approaches infinity. So there goes one horizontal asymptote. All right. Uh, is that it? Absolutely not. We need to check the limit as x approaches negative infinity. So, and you just see what we get, okay? Because you could have two distinct horizontal asymptotes. So I want to find the limit as x approaches negative infinity of the square root of 8x to the 6 minus 4x to the fourth over x to the third minus 2x. When you're going to negative infinity, it's the same procedure for polynomial functions. You focus on the terms with the highest degrees, the leading coefficients, or the leading terms. So this is the leading term in the numerator, leading term in the denominator. So that's what we're going to focus our attention on. All right, so let's extract them. And now this problem now becomes um, the limit as x approaches negative infinity of the square root of 8x to the 6th divided by x to the third. All right. So when we simplify it out, the same procedure, we're going to have limit as x approaches negative infinity. Now the square root of 8 is 2 root 2 times the square root of x to the 6 is going to be the absolute value of x to the third. Absolute value of x to the third over x to the third. Okay? All right, now what we're going to have next, let's use a constant property of limits. So you can factor out the constants because it's independent of where x is gone. So 2 root 2 of the limit as x approaches negative infinity of plus or minus x to the third over x to the third. Okay? Now since you're going to negative infinity, this absolute value is going to take the negative sign. So it'll be 2 root 2 times the limit as x approaches negative infinity of negative x to the third um, over x to the third. And you see that this divides out to negative 1. So our limit is simply going to be 2 root 2 times negative 1, which equals to negative 2 root 2. Okay, so what does this tell us? It tells us we have two horizontal asymptotes. So the horizontal asymptotes are y is equal to negative 2 root 2 and y is equal to 2 root 2. All right, so there goes your horizontal asymptotes. Now, next thing we're asked to find, we're supposed to find the vertical asymptotes and use limits to verify the accuracy of our results. All right, so our vertical asymptotes are our infinite discontinuities. Okay, so let's rewrite the problem. So what we're looking for the vertical asymptotes now, vertical asymptotes. So what we're going to do is make sure we eliminate the removable discontinuities first before we start to look for our infinite discontinuities, which are our vertical asymptotes. Okay, so the original problem we have the function f of x equals the square root of 8x to the 6th minus 4x to the 4th, and that divided by x to the third minus 2x. Okay, let's make sure that there are no removable discontinuities first. So we have to simplify the top as much as we can, see if it cancels out anything in the bottom. And then what's left in the denominator, we can set to 0 to look for our vertical asymptote. So in the top, we can factor the numerator. By all means, we can take out 4x to the fourth And then we're going to be left with 2x squared minus 1 in the numerator. And in the denominator, we also have to factor to see what can be canceled out. So in the denominator, we can factor out x squared. So we have x squared times x minus, I'm sorry, we can factor out x, not x squared. So take out x, and then we're left with x squared minus 2. All right. All right, the numerator, if we root both of them, we're going to have the absolute value of the square root of 4 is 2. The absolute value of 2x 2x squared times the square root of 2x squared minus 1 divided by x times x squared minus 2. Okay? Now, we can completely reduce this. This x can reduce this. It doesn't affect the sign anyway. So this becomes 2x, because this is x to the 1. And I can cancel this x with that, with one of those powers. So you subtract 1, you're left with just the absolute value of 2x times the square root of 2x squared minus 1 divided by um, x squared minus 2. So what does that tell us? It tells us that there is a removable discontinuity at x equals 0. We don't want to include that, okay? All right, now to find our vertical asymptotes, what we'll do is set the denominator to 0, and that's solve for x. So x squared is equal to 4. Take the square root of both sides, and then you have the absolute value of x is equal to 4. So this tells us that x is equal to plus or minus, I don't know where 4 came from. That's supposed to be 2. Square root of 2. So root 2, so plus or minus root 2. Okay, so these are our vertical asymptotes. So vertical asymptotes is x equals negative root 2 and x equals root 2. Okay, so let's verify that these are vertical asymptotes. If they're vertical asymptotes, then the limit as x approaches this value from either direction will be um, infinity. It will suffice to just focus on one direction, because if it approaches infinity or negative infinity from one direction, then that is automatically a vertical asymptote. Okay, so let's go ahead and do the test with limits. Test with limits. All right. So let's start with the first one. So with the first one, we're gonna find a limit as x approaches uh, negative root 2 from, let's do from the right for both of them, okay? All right, so I want to I want to focus uh, on the reduced form of this problem. So let's see, let's take that piece right there. Absolute value of 2x times the square root of 2x squared minus 1 over x squared minus 2. Okay? All right, so let's simplify that. We're going to have 2 times uh, 2 times negative root 2 from the right times the square root of 2 times negative root 2 squared minus 1. And this whole story divided by um, negative root 2 square, negative root 2 from the right square minus 2. Okay? All right, so this is going to become negative 2 root 2 times the square root of negative root 2 squared is just 2. 2 times 2 is 4. 4 minus 1. Over in the denominator, you're going to have negative root 2 squared is just 2 from the right minus 2. So what is that going to become? If we simplify it, we're going to have negative 2 root 2 times the square root of 3 divided by, this will become 0 from the right, a very small positive number. So that becomes negative 2 root 6. 0 from the right can be written as 1 over infinity, right? And then it becomes negative 2 root 6 times infinity, which equals negative infinity. So that automatically shows that this is a vertical asymptote because it approaches negative infinity as x approaches negative root 2. Okay. All right. So before we do the next part, just a real quick correction. There's absolute value here, so I need to put in the absolute value. We don't want to forget that. So absolute value. So when you take the absolute value of negative 2 root 2, that makes it positive, right? So let me just take that minus out of there. So it's actually infinity, not negative infinity. Let's see. Not infinity, so let's see. Hello? All right, so just take out a negative positive, so that goes to infinity. So we see that that's a vertical asymptote. If it goes to plus or minus infinity, that's sufficient to conclude that it's a vertical asymptote. All right, so let's go ahead and test a limit from the other direction. Limit as x approaches root 2 from the right. We're testing the second vertical asymptote that we have to see if the function approaches infinity. Okay, so the absolute value of 2x times the square root of 2x squared minus 1 over x squared minus 2. It's basically going to be exactly the same thing. The only difference here is that this will be positive instead. So this is, I could skip some steps. Could go right here. It's going to be absolute value of 2 root 2 times the square root. You know what? Notice when you square negative root 2 or positive root 2 is the same thing. Okay? So this is still going to be a 4 regardless of the sign, minus 1 over, in the denominator, if you square negative root 2 or positive root 2, you get the same value, which is 2, but we are approaching from the same direction, so it's a 2 from the right, minus 2. Okay? You can go through the mechanics to verify that this is correct if you want. So it's going to become 2 root 2 times root 3, as we determined earlier, over 2 from the right minus 2 is a very small positive number, equals 2 root 6 over 0 from the right can be written as 1 over infinity. So this equals 2 from the 2 root 6 times infinity. When you multiply the numerator by the reciprocal of the denominator, so your final answer is going to be infinity. Okay? So since the limit as x approaches plus or minus root 2 of the function equals infinity, that implies that plus or minus root 2 are vertical asymptotes. Okay, this is basically what the definition of vertical asymptotes are using limits. If it approaches that particular value and the function goes to plus or minus infinity, then that is a vertical asymptote. In this case, they will go to infinity, which is sufficient. All right, let's take a look at question number 3. So for question 3, we are to find the approximate uh, slope of the function f of x equals x squared. The approximate slope at x equals 2 by finding the average rate of change on uh, 1 comma 3. Okay, in this case we're going to be using the secant line. All right, the secant line to approximate the slope. Okay, and then this is the a part, and then in the b part you're going to find the slope at x equals 2, or the instantaneous rate of change. Okay, so find the instantaneous rate of change um, at x equals 2. So in option B, we're going to be looking for a tangent line, of course, at that point, since the line is intersecting the curve at only one point. And the expectation is for you to find instantaneous rate of change using the limit definition of instantaneous rate of change f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay? All right. So let's start with the a parts. Let's find the average rate of change. Average rate of change. Okay, average rate of change on 1 comma 3. You want to note that these are x values, okay? So I'm going to call this AB. These are x values. That's why they're in brackets, not in parentheses. So please do not call this x and y. That's inaccurate, okay? So average rate of change is basically delta f over delta x. And you can find that on an interval by computing f of b minus f of a divided by b minus a. Okay, this is how you find the average rate of change. In this example, f of x is equal to x squared. All right, so let's go ahead and do it. So b is 3, so f of 3 minus a is 1 minus f of 1 over 3 minus 1. All right, now we're going to input this independent values into our function. So we're going to have 3 squared minus 1 squared, 3 minus 1 is 2. So 3 squared is 9 minus 1 over 2. 9 minus 1 is 8. 8 over 2 equals 4. All right, so there goes the average rate of change. Um, Basically, we're approximating the rate of change at x equals 2 on the interval, using the interval 1 to 3. So let's write down what our answer means. So approximate rate of change, same thing as slope, right? Or slope at x equals 2 of f of x is equal to 4. Okay, so this is an approximation. It could be a good approximation or a terrible one, but it's just a secant line, so it gives us a general idea. All right, so for B, we would need to find the instantaneous rate of change now. So instantaneous rate of change. We don't need an interval because at an instant, all we need is a point. So at x equals 2 in this case. Okay, so instantaneous rate of change is df dx, which is the same as f prime of x, and is the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, in this problem, we know that f of x is equal to x squared. All right, so let's go ahead and do this. So inputting f of x into this situation, x squared, this is going to become the limit as x approaches 0 of x plus h squared minus x squared over h. Okay, now this will give us the equation for, or the function for the rate of change at any x value. Then when we're done with this whole procedure, we're going to pin our rate of change to x equals 2 by plugging in 2 into the resulting function. Okay, all right, let's simplify this. We're going to have the limit as x approaches 0. If you expand this component, you have x squared plus 2x h plus h squared minus x squared over h. Now the x squares cancel out. So this is going to become the limit as x approaches 0 of, we can factor out the h, right? Of h times 2x plus h over h. Okay? Now, you can see why we didn't bother plugging in 0 for h from the onset, because we would have had a 0 in the denominator, which is we can actually evaluate. So we have to simplify it as much as we can. And remove removable discontinuities, as we can see here that h equals 0 is a removable discontinuity. So let's go ahead and take that out. Take out h. So now we're going to have the limit as x approaches 0 of 2x plus h. We can now input h into our function without any complications. So we have 2x plus 0, which is just 2x. So this tells me that the function that represents the instantaneous rate of change of the original function, f of x is equal to x squared, is 2x. Okay, so this is f prime of x. All right, so now we have to pin it at the specified x value. We have to find the instantaneous rate of change at x equals 2. So we're going to evaluate f prime of 2 by inputting 2 into our function. 2 times 2 equals 4. So the instantaneous rate of change of the function f of x equals x squared at x equals 2 is equal to 4. Okay, this is a coincidence. In this case, the approximate and the instantaneous rate of change are the same. So this is a perfect approximation. But it's not always the case, okay? So this is just coincidence. So don't always expect that the slope of the secant line matches the slope of the tangent line. This is just a coincidence. In some cases, that's the case. In other cases, the approximation is terrible, but the instantaneous rate of change tells you exactly what the slope is at the particular point. All right, so there you have it. All right, let's take a look at question number 4. So question 4. You're to use the limit test to determine if the given function, function is continuous at x equals 0. Okay? And the function is a piecewise defined function given by f of x equals sine x over x. When x is less than 0, function is equal to 1. When x is equal to 0, and sorry about this, I'm going to try this well. And the function is x to the fourth plus x to the third um, over x to the third when x is greater than 0. All right? So this is the piecewise defined function that we're going to be focusing on in this problem. All right, so let's go ahead and start testing. Okay, so let's start from test number 1. So test I, we have to show that the function is defined at the specified x value. Okay, so that's we have to show that f of 0 exists. Okay, because we have to prove continuity at x equals 0. So we have to part 1. Test number 1, we have to show that the function is defined at that specified value. So what is f of 0 in this function? In this function, f of 0 is clearly 1, so we see that it is defined in this piecewise defined function. All right, test 2. For test 2, we have to show that the limit as x approaches the specified value 0 of the function exists. Okay, we have a piecewise defined function here. So we're going to be using two different functions as we approach the specified x value from both directions. So let's draw a number line to order our functions. So the specified value that we're going to be approaching is 0. To the left of 0, less than 0, this is the function that's active. To the right of 0, this is the function that's active. All right, so we have to evaluate the left and right hand limits. All right, so let's start with the left hand. All right, left hand. Okay, so um, the limit as x approaches 0 from the left of the function is the same thing as the limit as x approaches 0 from the left of sine x over x. And using the squeeze theorem, we know that this is equal to 1. All right? So let's find the right-hand limit. If they're both the same, then we can conclude that the limit, in fact, exists. All right? So the right hand. All right, so for the right hand, we have to show that the limit as we have to find the limit as x approaches 0 from the right of the function. And that's the same thing as the limit as x approaches 0 from the right of x to the fourth plus x to the third over x to the third. We can see here that if we plug in 0, we'll have some complications, and the denominator will have 0 there, and we can divide by 0. So let's go ahead and factor the numerator and then reduce. Okay, so limit as x approaches 0 from the right, factor out x to the third, so you're left with x plus 1 over x to the third. And what you see happening here is some cancellation action. This cancels with that. So this limit becomes the limit as x approaches 0 from the right of x plus 1. And then when we plug in 0, it's just going to become 0 from the right plus 1, which is just 1. All right, so since the left and the right hand limits are the same, we can conclude that the limit does exist. Okay, so since the limit as x approaches 0 from the left of the function is equal to 1, and that is equal to the limit as x approaches 0 from the right of the function, that implies that the limit as x approaches 0 of the function exists. So this function passes test number 2. All right, so test number 3, last but not the least, test 3, we have to show that the limit as x approaches the specified value 0 of the function that we just determined in step 2 is equal to the value of the function at a specified x value f of 0 as determined in part 1, in test 1. So is that the case? Absolutely. Because we just determined that the limit as x approaches 0 of the function, the left and right hand limits are 1, so the double-sided limit is 1. And that is also exactly what the value of the function is in test number 1. Okay, so it passes test 3. So what's our conclusion? The conclusion is that the function is continuous, at x equals 0. All right, so there you have it. All right, let's take a look at the last one, problem number 5. So for problem 5, we're to find the value of a um, that makes f of x continuous. Okay, so what on earth is f of x? So let's write down what f of x is. F of x is a piecewise defined function given by ax plus 5 when x is less than or equal to 2, and x squared plus 5 when x is greater than 2. All right? So the question is, what value of a will ensure that this function is continuous? So the function is continuous. We know that the left and right hand limits is going to be the same. And since 2 is included in the left hand function, then that also covers the whole idea of the function being defined at that value. Okay? So let's do it. So all you simply do is you're going to plug in this value into these two functions and set them equal to each other. Okay? So we're going to do, let's see, a times 2 plus 5. It has to be equal to 2 squared plus 5. Okay? So what did I just do? I substituted 2 into, let me show you some arrows. Take this 2, and I input it into the function to the left, and then these 2 into the function that on the right. So I'm trying to force them to be the same, okay? All right, so that will make it happen. So let's solve this resulting equation for a. So we're gonna have 2a plus 5 equals 2 squared is 4, 4 plus 5. that yields 2 and 2a plus 5 equals 9. You can subtract 5 from both sides. You have 2a equals negative equals 4. 2a equals 4. Divide both sides by 2 and you end up with a equals 2. So this value will make the function to be continuous. But thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel by clicking down the subscribe button. You can post the comments to let me know what you think about this tutorial. You can like it or share it via your individual social networking program. More clips like this can be found at mathgotserved.com/calculus, or just scan this QR code for direct access to a whole collection of calculus tutorials such as this. Thanks again for watching.